Welcome once again for this lecture of electronic circuits. So we are discussing here about the switching regulators. So second type of this switching regulator is the boost regulator. That is also called as the step up converters. So if we would be see about the step up converters, this is the diagram that we have also discussed yesterday. Now I would be just tell you some key points of this particular diagram. You can see in this particular diagram, uh, the position or the location of the inductor is little bit changed as compared to the buck regulator. It is now directly with the input supply. It is the DC voltage VI, and it is now directly connected to the VI, and it is in series with the catch diode. You can say the D1. Okay, and the controller or the switching circuit would be now here is connected across the input voltage. Okay, or it is in parallel. You can say the inductor, and the collector terminal is connected to here. The it is given as a terminal number A, where we have to be calculate the voltage VA. Okay, and the base is again it is nothing but a PWM output that is coming from the controller circuitry. Uh, all of you are aware of that from the block diagram and the circuit diagram of the SMPS. And the emitter is connected to the ground connection. Now the polarity of the D1 would be very much clear that it is an anode and it is a cathode. So anode would be always positive and cathode is always negative. But we would be see how it would be change its polarity according to the operation of the circuit. Now the other part of the circuit is the capacitor C1 is connected across this load as usual, and this is R1 and R2, that is a parallel network that is actually provide a feedback path to this controller circuit as per the uh, basic circuitry of the SMPS. Now the output current that would be flow at the load would be that is I0, and the voltage across the load would be V0. Okay, so this is the basic arrangement of the boost regulator or step up regulator. Now that is I have written here. Okay, so a step up regulator, a boost converter would be produces the DC voltage that is higher than the supply voltage. That's why it is called the step up converter. Okay, and the position of this all components are mentioned here. Now come to the operation. Directly we have to be come to the operation of this particular circuitry, that is a boost regulator. Now when you have to be discuss about the operation of this, you would be find out that this is the DC voltage input voltage. Now it would be start to flow of the current across the inductor, that is IL in this direction, the direction as shown in the diagram. And because of this current flow, you can see the polarity of the inductor also. There is a positive is at the left end and the negative at the right end of this inductor. So current would be flow across this inductor, and now the transistor switch is closed. So whatever it is biased in the saturation region because it is a BJT. The voltage across this particular switch would be nothing but this is the DSAT, that is a cut-in voltage of this transistor. That will for the silicon based transistor mainly 0.6 volt or 0.7 volt, and we have to be also see the voltage available at this terminal A, that is nothing but the voltage across the switch. And now because of this condition, in this condition we have turned on the switch Q1. So what happens, as per the polarity of this inductor, negative terminal at this end, right end, so the polarity of the diode would be also as shown in the figure, means negative would be available at the anode and positive would be available to the cathode. So this kind of the polarity would be make the diode D1 is reverse biased. So it would be now reverse bias, and we know that ideally in the forward bias it would be act as ideal switch, and in ideally reverse bias it would be act as an open switch diode. But practically there would be a little bit leakage current would be flow, that would be negligible amount. Okay, so in this condition what happens, it would be act as an open circuit you can consider, and the remaining network of this circuitry is the output network, where we can see the C1 and the load is there, and the voltage across the load is V0, that is a fixed output voltage and DC voltage, and there is a current I0 is keep flowing across this load. So I0 would be start to flow from this capacitor and it would be end to this. Okay, someone has doubt yesterday that why when it is open, then how the current would be flow. So till the Q1 is on, your D1 would be reverse bias and it would be open. It would be not establish any connection between the one part of the circuitry to the another part of the circuitry. Till duration of this, what happens? Whatever the charge stored at the C1, it would be hold the responsibility on this particular capacitor to provide the current to this load. Okay, so the current would be still flowing through this particular load, that is I0, and at this moment you can say that our capacitor C1 is discharging. Okay, and now we again come to this part of the circuitry. If you have to be see, one current IL is flowing across the inductor, and that would be flow in this particular direction in this particular loop across this switch. Okay, so what happens, as we have to be see, the network is very much ideally it is would be keep increasing the current across the inductor. Why? Because we know that inductor is also a charge storing device. So when the current would be start to flow across it, it would be start to charge. So now your inductor is starting to charging. So your current across the inductor would be linearly increasing. Okay, and whatever the voltage across this particular voltage drop would be occurred at this inductor would be, you can easily calculate on the applying the KVL, that is rise in potential, that is plus VI, then drop in potential minus VL, then drop in potential minus VSAT. I think all of you are aware of that how this writing this plus and minus sign. So whenever you can, assumptions are there actually. If you assume that all the rise in potential would be considered as a positive and drop in potential as a negative. So here you can see the VI is, you are moving from negative to positive, means it is rise in potential. And when you are moving positive to negative means drop in potential. So all this drop in potential would be indicated by the negative sign, and rise in potential would be indicated by the positive sign. So what is the voltage across VL? Inductor, that is VL is equal to VI minus VSAT. Okay, so this is the amount of voltage available across this particular inductor. Okay, now this is the first condition that boost regulator will be operated when your switch Q1 is on. That is I mentioned here, D1 is reverse bias and VL is like this. So based on the inductor equation, the current also you can find out this across the inductor. I have told you that it is linearly increasing with respect to time domain. So till your switch is on, your current is keep increasing across the inductor, that is shown in this particular equation. Also you can say the ILT, it is time depending current. So it is only increasing for T on time. So inductor current at the steady state, when we have not start to calculate the timing, and plus it is nothing but the voltage across it, that is VI minus VSAT upon in L1 inductance, and this is the T, here it is nothing but the T on. Okay, so till your current is linearly increasing, that is also understood from with this equation. We would be verify this through the waveform discussion. Now come to the second condition. The second condition is what? When your Q1 is off. Okay, so you can see here, when your Q1 is off, your switch would be off, it is open. Now switch is open, so no current would be flow across this switch. So whatever happens here, all the current would be now follow this path. But the problem is that in the previous case, the polarity is different. Here the positive is at the left hand side and negative at the right hand side, and now your switch is open. Okay, this is the condition when your switch is open. Then what happens? Inductor having the property, it would be keep flowing the current across it. To keep this circuitry operative, your inductor current should be flow, and for this purpose what happens, your inductor would be reverse its polarity. And when the inductor would be reverse its polarity, you can see now the left hand side there is a negative and right hand side there is a positive sign is there. Now we have seen that inductor has reverses its polarity. Your inductor current would be keep flowing across the inductor, and it would be now, you can see, because of this reversing of the polarity of the inductor, the polarity of the across the diode, it would be also changed. And you can see now anode is positive and cathode is negative, as usual regular operation of the diode. Now you can say this diode would be having forward biased, so it is operating in the forward bias condition. Now this current IL would be flow through the diode also, and because diode would be acting as a switch in the forward bias condition, and you can see that there is a load current is also flowing across this load. At that moment, what happens? We know that in this condition, the inductor current would be now operating to or you can say the inductor is also the charge storing device. Now inductor would be start to discharge it. Okay, and at that moment capacitor would be start to charging. Okay, and whatever the inductor current would be start to decrease now, and it would be discharged to capacitor, means inductor is discharged to capacitor, means capacitor is start to charging, and it would be also the rest of the part of the current would be available to drive the load. Okay, so now IL would be distributed into two different sections. One is busy with the charging of the C1, and another is maximum current is actually used to regulate the or driving the load. Some amount of current is available to charging the C1. Okay, so this is in the condition of the reverse bias mode. Sorry, in the condition when the Q1 is off. Okay, now we have to be calculate the voltage across the inductor. You can easily calculate by following this loop. Okay, so in this condition, you can say VI, then plus VL, because it is again rise in potential, then drop in potential across the diode VF, and that is minus V0 is equal to 0. So you can see that what is the V0 is here. V0 would be VI plus VL minus VF. You can see now the term here VI plus VL, and VF is very small as compared to the VL and VI. Okay, so it is rise in voltage, means it is step boosting the voltage. It is more, V0 is greater than this VL. Always remember that V0 is greater than this VL, and VI plus VL is what? It is the voltage available at the switch or A. So VA is equal to what now? It is VI plus VL. Okay, so this is the equation that is I have also mentioned in the next slide also. The V0 is VI plus VL minus VF. The current flowing in the inductor during the T off, which is ramping down, and it is computed at, because current would be start to decrease now in the T off duration across the inductor. So IL would be I T on plus the voltage across the inductor upon inductance and the T off. This T is now, it is the T off time. Okay, small t is nothing but it is the T off time. Okay, so voltage, you can see this is the main equation that we have to be consider here. This your output voltage is now increased, or it is larger than the input voltage. That is our main purpose, to boost up the input voltage. So here we are conversion of DC to DC, but we are boosting the level of the DC voltage. Okay, that's why it is called as a boost regulator or step up converter. Okay, I hope now the idea is clear from this description, and that you can also verify with the help of this waveform. Step up converter waveforms are available here in this particular slide that we have discussed yesterday also. This is the VA, means the voltage across the switch during the Q1 is on and Q1 is off. So T on means when the Q1 is on, and T off means when the Q1 is off. Okay, so in this case you can see during the transistor switch is on, voltage of the transistor is very less, and it is positive but very less. It is nothing but this is the V side. That's why this level is shown here. Okay, and at that moment when the T on or Q1 is on, your inductor current is positive, and it is nothing but VI minus VSAT that is available here, that is shown here above this ground potential. And at that moment your inductor would be start to charge. So the current across the inductor is linearly increasing. Okay, that is shown here, and it would be reached to the maximum value I peak also, and the output voltage would be remains constant. So it would be always shown this particular this line. This is output voltage level. It would be constant. So there is some discussion that we have to be also discuss. When your IL is less than I naught, what happens? When it would be more than I naught, what happens? You have to see. And now you can see that during the T on period, your voltage V naught is little bit decreasing from its base level or constant value. Okay, and actually this decrement is very small. That is a ripple voltage level. Ripple level is there in point some millivolt, but we have to be just shown here. So your output voltage starts to little bit decrease during the T on period because at that moment there is diode D1 is reverse biased and there is no direct current is available to increase the output terminal voltage. So load is driving with the help of the whatever the charge is, whatever the current available at the capacitor, and capacitor is discharging at that position, means your voltage is keep decreasing and decreasing across the load. That's why it is showing as a decreasing phenomena here. Okay. Now come to the second condition when Q1 is off or controlling switch is off here. So at that moment what happens? Your voltage across the VA would be increased from VSAT, it would be increased to the VI plus VL. We have already seen in the equation also, it would be now increased to the VI plus VL, that is shown here. That is the positive voltage now across the this particular switch. Okay, now you can see here VL is now decreased and it will be goes to the negative because the polarity of the inductor is changed. That's why it is V0 plus Vf is the voltage across inductor, but is negative in polarity. That's why it is shown below the ground signal. Okay, this is shown below the ground signal. Okay. Now we have to know that as in this the case when the switch is off and T off period, what happens? The voltage across the inductor is negative, so your current across the inductor would be start to decrease now. Now the position, now the condition we have achieved when the inductor would be start to discharge, and this discharge current would be driving the load as well as the capacitor also. Okay, so you can see that in this case during T off period your current is start to decrease. Now during the current IL is start to decrease, what happens? It would be now start to charge the capacitor as well as it would be driving the load. The voltage across the output load is or output voltage or the capacitor voltage V0 is nothing but the voltage across the capacitor as well as the voltage across the load, because both are in parallel. So it would be what happens, your output voltage would be start to increase here, but it would be keep increasing only when your IL is greater than I naught. Once your IL is less than I naught, okay, because your IL is keep decreasing, it is discharging. So when it would be once it would be below the level of output voltage of current across the load, then what happens? Your voltage across this load would be again start to decrease. Okay, and it will be decreased up to the maximum VR, that is a rippled voltage, ripple level. Okay, so this is the operation of this boost regulator during the T on and T off period. So we have observed the switching output voltage, inductor current, as well as the voltage output voltage of this particular circuitry. But the main outcome is what? Your output voltage is increased in amplitude as compared to the input voltage during this operation of the boost regulator. Okay, so I hope the function is clear now. Now come to the one of the you can say similarly as yesterday we have shown the video. It is one of the another video is available for the boost converter. I will be just show you by sharing the video. Okay. Now you can see the video of the boost converter. When the T on is on, then what happens? The current is flowing in this direction off, and this is flowing through the diode and through the load. Okay. And your ripple voltage is also shown. That is how the ripple voltage is generated here. So this is the keep on off conditions are there. So you can see during the on condition what happens, and during the off condition what happens is there. You can see here when the switch is on, the current path is in this particular direction, as well as the capacitor would be driving the load. But when it would be goes into the off condition, then the current path would be changed. Now it is some part is going to capacitor and then the rest of the part to the load. Okay, so this is the way that it would be actually work. Okay, I hope now you are more clear that how this particular boost converter would be work through this animation. Okay. Now I would be again share this. There is some issue. Just a minute. I'm going to resolve it. I think all of you have just noted down this particular circuitry. Of PPT, there is some issue regarding this sharing. Okay, so now you can see we are discussing about the inverting regulator. That is, this is the diagram or circuit diagram of this inverting regulator. If you have to be see, I hope is the diagram is visible to you now. Please anyone reply and confirm me.
Yes, sir.
Okay. So this is the buck boost regulator or the inverting regulator. You can see now the arrangement is little bit changed. If you have to be seen this particular condition. In this way, if you have to be see here, the switch is now connected directly to the input circuitry, where the collector, if you have to be see here, in this particular case, collector is connected to the input side and emitter is connected to the in series with this inductor, and as usual we are giving the PWM input is here. Now if you have to be see, in this particular case, this is the PWM input and this is the emitter terminal and this is the collector terminal is there. Okay, and now the inductor is connected across to this particular input. So the position of inductor is now changed here. Diode is connected in such a way that when it would be switch is on, it would be reverse biased. When the switch is off, it is forward biased. and other connection is as it is in the previous boost regulator and the buck regulator. Okay, so there is no change in the other connections. All the connections are as usual. Now, when you have to be see the operation of this particular flyback converter, you can say, or you can say inverting converter. There's a different names are there. Buck boost regulator. There is a three names are there. So this circuit would be produced. The main element is that this circuit would be produced with the negative DC output voltage from a positive supply. That's why it is referred as a inverting converter, because it would be produced the output voltage that is opposite in sign with respect to the input voltage sign. So here you can see L1 is connected between the ground and the emitter terminal of Q1, and D1 is in series with the Q1 emitter as well as the capacitor C1. Now we have to see the operation of this particular converter. So this is the first condition when you have to see that the operation of this inverting converter when your transistor switch is on. What happens when the switch is on? Then again the voltage across it is plus there is a VSAT, as we know that, and the polarity of this inductor would be as it is, plus is above and negative is at the ground end. Okay, so at that moment your diode is reverse bias. Okay, because there is a cathode is again positively charged and anode is negatively charged. So it would be again a reverse bias condition. No current would be flow across this diode. So the current would be flow across this particular load would be that is through this capacitor, as in the previous case. But the direction of current you can see now it is little bit different. Okay, so because of this negative terminal, what happens? The direction of flow is opposite, and the polarity of the output voltage is also reversed. Now, if you have to see what is the voltage, as we know that the current is flowing across the inductor. So what is the voltage across this inductor now? Okay, so you have to be apply the KVL again. So what do you able to find? VI minus VSAT minus VL or VA, because here VL and VA is same, is equal to 0. So what happens? VL is equal to VI minus VSAT. Okay, and what happens when the switch is off? Let us see the current equation as per our discussion. So VA is nothing but a VL here, and it would be nothing but your VI minus VSAT. When the Q1 is off, so your VL, this VL would be reverses. To keep the flow of the IL, what happens? VL would be reversed, and VL is reversed. Then what happens? Your diode D1 would be now forward biased. Okay, and when it would be forward biased, then what happens? It would be produce a voltage that is V0 is equal to, here it is a positive sign. Remember, I have just forgotten here. V0 is equal to minus VL plus VF. So here there is a positive, negative voltage available here across this output terminal. That is the summation of the inductor plus voltage across diode. Okay, so output voltage is negative, and this output voltage level is depend upon the set of the choice of the R1 and R2 as per the basic circuitry of your SMPS. We know that. So you can see the condition when your switch is off. You can see here in this particular diagram. At that moment, what happens? The polarity of the inductor would be changed, as the polarity of the diode would be changed. It would be now forward bias, and the current direction would be see here. This is the way that the current is flowing across the diode and this load. Okay, and this inductor. Okay, so in this way we have to be find out this output voltage is nothing but VL plus VF minus of VL plus VF, negative voltage. Okay, now we have to be clear our whatever the discussion here with the help of the waveforms. So waveforms are very much important here. So here you can see that in this particular waveform, what is going on? In this case, during the two conditions, when the Q1 is on, that is the T on time, and during the Q1 is off, is the T off time is there. So when the Q1 is on, the voltage across inductor is what? Vi minus Vz, that is shown here. Okay. And at that moment, what happens? The current across the inductor would be keep increasing and increasing. Okay. So it would be charging the inductor. At that moment, your voltage is shown as it is rising in this way. Now, what happens when your voltage would be when your transistor Q1 would be off? Then what happens? Your voltage across the inductor would be reversed. In its polarity, it would be become now negative. Okay, so it would be now become minus V0 plus Vf. Okay, that would it would be shown below this ground. Okay, all of you please start to fill up your attendance on the chat box. At that moment is what happens, your inductor current would be start to decrease because it would be now discharging, and at that moment what happens, your capacitor would be start to charging, and because of this discharging current it would be again also driving the load as well. Okay, so at that moment you can see till your IL is exceeded with the I0, it would be decreasing, and when it would be go below this I0, it would be start to again increasing the output, rising this output voltage. Okay, so this is the all about this particular inverting converter. Well, the main thing is that the you have to see the output voltage would be now inverse in polarity, or inverting as compared to the input voltage. So V out not is now negative of the V in. Okay, that's why it is called the inverting converter. Its another name is buck boost regulator also, as well as you can refer it as a flyback converter also. So at the end of this lecture, I would be just show you the comparison of this particular linear power supply and switch mode power supply. So I have taken some points where we have to be discuss the comparisons based on the dropout voltage across the regulator. So you can say the in the case of the linear regulator input frequency 50 to 60 Hz. In the case of switching mode regulator is some kilohertz to megahertz. It is more. Efficiency is low in the case of linear regulator, 25 to 50% only. In the case of switching regulator, it is 65 to 75%. Then in the case of load regulation, it is linear regulator is better. Then in the case of line regulation, again it is linear is better than the switch mode power supply. Ripple voltage is less in the case of linear power supply, but it is more in the case of switch mode power supply, as well as you can say the size of is more as a case compared to the linear power supply, but switch mode power supply is smaller. Then the EMI electromagnetic induction is low in the case of linear power supply. It is more in the switch mode power supply. Similarly, the transient response is if you have to be see a linear power supply, it is faster, and SMPS is a little bit slower as compared to this. Complexity, if you have to see, linear power supply is simpler and SMPS is complex. So this is all about the SMPS and the voltage regulator. So this is the end of the third unit. Thank you all of you for attending the lecture. From Monday we will be start the fourth unit, that is op-amp.